So today we're going to be solving October-November 2020 paper 42. Okay, I'm going to start with question number 1. The rate of the reaction H2 and I2 to form hydrogen iodide is studied. A small amount of H2 is mixed, or hydrogen gas is mixed with a large excess of gaseous iodine at a temperature of 400 Kelvin, and the reaction is monitored. The graph obtained is shown. Here they're measuring the relative concentration of hydrogen gas, okay, against time in seconds. Suggest why a large excess of iodine is used in this experiment. So over here in this experiment, you're trying to study the rate of the reaction, okay, with respect to the concentration of hydrogen gas. So you want to ensure that the iodine concentration may affect the rate of the reaction. So you want to make sure if you use a very large amount over time, even though the iodine is consumed, because a very small amount of iodine is consumed relative to how much we were using, we can assume that the concentration remains constant. So in other words, we're trying to ensure that the iodine concentration isn't affecting the rate. We're using a very large concentration, so it remains relatively constant, okay? There's a very small change in the iodine concentration. So here essentially only hydrogen gas will be affecting or the concentration of hydrogen will be affecting the rate, okay? So the idea here is that, so the concentration of iodine remains constant, okay, or relatively constant. The reaction is first order with respect to hydrogen gas. Use data from the graph to confirm this statement. All right. So if you look at the graph, right, if you have a first order reaction with respect to a particular reactant, what property does its half-life have? It has a constant half-life, right? So for example, over here, if we look at the starting concentration, relative concentration of hydrogen is 8. Let's see the amount of time it took to go from a concentration of 8 to a concentration of 4. Right? To go from a concentration of 8 to a concentration of 4, it took us roughly 44 seconds or 48 seconds over here, right? And then if you look at the amount of time it took to go from 4 to 2, the amount of time it took to go from 4 to 2, right? That comes out to roughly 96 seconds. So the half-life over here remains constant. The half-life remains constant. It's just 48 seconds. Every 48 seconds, the concentration of hydrogen is becoming half, right? So we can say over here that it is first order, okay, with respect to hydrogen because it has a constant half-life of 48 seconds. Therefore, it is first order with respect to hydrogen gas concentration, okay? Here in this particular question, okay, every little square over here is 4 seconds. So here 48 seconds, we have 40 plus 8, and then we have 92, and then, okay, or about, sorry, over here it comes out to about 94. Here it actually comes out to about 94 since it's between 92 and 96. So you get a half-life of 46 in the second one, but it's roughly the same, right? 48, 47. There's a range of answers that they'll accept over here, okay? There's a range of answers that they'll accept over here. So we've just said 40, 48, that's fine, okay? In this particular question, you get a mark for drawing these constructions lines and showing you're working on the graph for the half-life, and then also for stating that the constant half-life means that it's first order. The next part of the question says, 3 separate experiments were carried out at 400 Kelvin with different starting concentrations of hydrogen and iodine. The results are shown in the table. Use the data and the order of reaction with respect to hydrogen gas given in A part 2 to deduce the order of reaction with respect to iodine. Explain your answer giving data in support of your explanation. Now, if you look at experiments 1 and 2, okay, let's just compare experiments 1 and 2. In each of these experiments 1, 2, and 3, we have different concentrations of hydrogen and different concentrations of iodine, right? Now, we know for a fact that it's first order with respect to hydrogen. We proved that from our previous part, right? By looking at the graph, by looking at the half-lives of hydrogen gas. Now over here, that means that the rate equation is in the form K times the concentration of hydrogen times the concentration of iodine. Okay. Now, to some power, we need to figure out the order with respect to iodine. So let's call that power x. Okay. Now, if you look at experiments 1 and 2, right? So let's say we're looking at experiments 1 and 2. Okay, we're looking at experiments 1 and 2. What we have is the concentration of hydrogen, okay, is multiplied by a factor of 10. Right? We have 1 into 10 to the power of -1 divided by 10 to the power of -2. So we're multiplying the concentration by a factor of 10. And the concentration of iodine is also multiplied by a factor of 10. You have 10 to the power of -2 divided by 10 to the power of -1. So in both cases, we're multiplying the concentrations by a factor of 10. And if you look at the rate, over here, okay, the rate is being multiplied by a factor of 2 times 10 to the power of -15 divided by 2 times 10 to the power of -17. So the rate is being multiplied by a factor of 100. Now we know that if I multiply the hydrogen concentration by a factor of 10, the rate will be multiplied by 10. And the overall rate is being multiplied by 100. So what is the effect due to iodine alone? Over here? Multiplying hydrogen by 10 multiplies it by 10, but the overall effect is times 100. So therefore, multiplying iodine by 10 also multiplies the rate by a factor of 10. So if I increase the concentration of iodine by a factor of 10, the rate is multiplied by the same factor. Therefore, we can say that the order with respect to iodine is 1. Okay. Use information from A part 2 and your answer to B part 1 to write the rate equation. So here we can say that the rate equation is the rate is equal to K times the concentration of hydrogen times the concentration of iodine. Okay. Use your rate equation and the data from experiment 1 to calculate the value of the rate constant for the forward reaction at 400 Kelvin. Okay. Include the units for K. So if you use data from the first experiment, right, we have over here rate is equal to, right, the rate in the first experiment is 2 times 10 to the power of -17. Okay, this is equal to K times the concentration of hydrogen in the first experiment, that's 10 to the power of -2, times the concentration of iodine, which is also 10 to the power of -2. So then what does K come out to over here? K comes out to 2 into 10 to the power of -13. Okay, and what are the units of K? Here everything is in seconds. Okay, so what we have over here is rate units are, the units of rate are concentration per second. Okay, the units of rate are concentration per second, right? That's moles per dm cube per second. And if you divide it by concentration squared, you're left with concentration to the power of -1 per second. So what you have is the units are moles inverse decimeter cube per second. All right, the next part of the question says, at 400 Kelvin, the rate constant for the forward reaction is approximately 1000 times greater than the rate constant for the backward reaction. The overall orders of the forward and backward reactions are the same. So they're saying both the forward and the backward reaction have an overall order of 2, right? Because the overall order here is the sum of the individual orders. So here you have order 1 with respect to hydrogen, order 1 with respect to iodine. So they're both order 2, right? That's the sum of the orders, so that's 1 plus 1. They're saying backward reaction is also order 2, forward reaction is also order 2. Use this information to explain what will happen if equal concentrations of Hi, H2 and iodine are mixed at 400 Kelvin. You should comment on the relative initial rates of the forward and backward reactions and the position of the equilibrium. So what you have over here is this reaction, right? And they're saying that at 400 Kelvin, the forward reaction is 1,000 times faster than the backward reaction. The forward reaction is 1,000 times faster than the backward reaction. So if I mix equal concentrations of all three of these, initially, if the forward reaction is 1,000 times faster than the backward reaction, right, where will the equilibrium move? Will it shift to the right or to the left if I mix equal concentrations? It'll shift to the right, right? Because remember, what's happening is once I mix equal concentrations, okay, they both have the same overall order. Because the forward reaction is so much faster than the backward reaction initially, right? The forward reaction will happen at a much faster rate, so there'll be a net formation of product initially. Eventually, we'll reach equilibrium, but what will happen is that hydrogen and iodine will initially react much faster, so the forward reaction, okay, will take place faster than the backward, so the equilibrium will shift to the right, okay. So we can say over here that if you talk about the relative initial rates of the forward and backward reaction, right? No, the forward reaction, okay, has a faster rate. Forward reaction has a faster rate, okay, than the backward reaction. Faster rate than the backward reaction. Than the backward reaction, and therefore the equilibrium will shift to the right. Equilibrium will shift to the right. At 700 Kelvin, the rate constant for the forward reaction is approximately 50 times greater than the rate constant for the backward reaction. Use this information and the information in C part 1 to deduce the signs of the enthalpy change values for the forward and backward reactions. Explain your answer. So over here, at 400 Kelvin, the forward reaction is 1,000 times greater. Okay, but at 700 Kelvin, the forward reaction rate constant is only 50 times greater. So then what does that tell you about the enthalpy change of the forward reaction? Let's say if I increase the temperature, the forward reaction is less favored. So therefore, we can say over here that the forward reaction, okay, the forward reaction is exothermic, okay, because an increase in temperature, okay, forward reaction is exothermic because an increase in temperature is decreasing the relative size of the rate constant. Here it's 1,000 times greater. At a higher temperature, the forward reaction rate constant is only 50 times greater. So we can say that forward reaction has a negative delta H, okay, and backward reaction has a positive delta H. Positive delta H. Now, how do we explain this? Go back to your equilibrium, okay? At 400 Kelvin, if you have equal concentrations, the forward reaction is 1,000 times more likely than the backward. The forward reaction has a rate that's 1,000 times greater than the backward, right? On the other hand, at 700 Kelvin, the forward reaction is only 50 times greater than the backward reaction. So relatively speaking, at 400 Kelvin, the equilibrium will lie further to the right, whereas at 700 Kelvin, because the backward reaction is more favored, it's endothermic, right? There'll be more concentration of reactants. So over here, we'll say that, okay, what will happen is, right, the equilibrium will lie further to the left. Equilibrium will lie further to the left at 700 Kelvin. Okay. All right. The next question that we have is question number 2. Okay. Write an expression for the Ka of the weak acid HA in terms of the concentrations of the species involved. So for a weak acid HA, right, the equilibrium can be written as HA dissociates to form H plus and A minus, right? Partially dissociates or partially ionizes. So what we have is the concentration of H plus times the concentration of the conjugate base divided by the concentration of the acid. The hydroxyl ammonium ion is a weak acid. A 1 into 10 to the power of negative 3 mole per dm cube solution of hydroxyl ammonium ions has a pH of 4.41. Calculate the Ka of HONH3 plus. So here, if we have to calculate the Ka of this weak acid over here, okay, what we have is we have the hydroxyl ammonium ion, okay, and this is the equation for the ionization. Okay. Now, let's say that at equal initially I have 1 into 10 to the power of 3, 10 to the power negative 3 moles per dm cube of this. Okay. And let's say initially I have 0 moles of this and 0 moles of this. Now let's say at equilibrium, right, the concentration of this changes by x. The concentration of this changes by x. So this decreases by x. So the concentrations of these two will increase by x, right? Now what can I assume about the concentration for a weak acid at equilibrium? If it's a weak acid, can we assume that the equilibrium concentration is the same as the initial concentration? Right? For a weak acid, we can assume that barely any of it ionizes, so the equilibrium concentration is the same as the initial concentration. And where we have x mole per dm cube of H plus and x moles per dm cube of the conjugate base. So here we can say that the Ka is equal to the concentration of H plus times the concentration of HO and H2, right? That's the conjugate base divided by the initial concentration of the acid. Okay. Now, they've given us the concentration of H plus here. That's just X, right? The initial concentration of H plus is, they said pH is 4.41. So the initial concentration of H plus is 10 to the power of negative 4.41. Again, the concentration of H plus is 10 to the power of negative pH. Okay. And obviously the concentration of the conjugate base is the exact same. It's also 10 to the power of negative 4.41. Divided by the concentration of the acid, we said at equilibrium is same as the initial concentration. That's 10 to the power of negative 3. So what is the Ka over here? The Ka comes out to 1.51 into 10 to the power of negative 6. Okay, moles per decimeter cube. Moles per decimeter cube because you have concentration squared divided by concentration. Okay, so the Ka over here is 1.51 into 10 to the power of negative 6 moles per decimeter cube. Okay, they don't really expect you to write the units over here. Okay, but I always write the units. They just want to know the value of the equilibrium constant. All right, calculate the pKa. The pKa is simply the minus log of the Ka, right? The pKa is simply the minus log of the Ka. So we have minus log of Ka, which will come out to 5.82. Okay. All right. The solubility product of manganese 2 hydroxide in water is 1.1 times 10 to the power of negative 11 mole cube dm to the power of negative 9 at 298 Kelvin. Calculate the solubility in water at 298 Kelvin. Okay. Solubility is basically, they want to know it in moles per decimeter cube. The solubility is how much dissolves. Okay. How much dissolves in moles per decimeter cube. How many moles dissolve per decimeter cube of water at 298 Kelvin. Okay. So let's say over here I have manganese hydroxide. Okay, I have manganese hydroxide, and right, if you look at the dissociation of this guy, this is what you have. Right now, they're saying we want to find out how many moles per decimeter cube of manganese hydroxide will dissolve. So let's say that x moles per decimeter cube dissolve. That's what we want to find. Right, that's the solubility. That means that at equilibrium, we're going to have x moles of this, and we'll have 2x moles of hydroxide, right? Now, if you look at the solubility product is the concentration of Mn2 plus times the concentration of OH minus the whole thing squared. The concentration of Mn2 plus at equilibrium is x, and we have 2x the whole thing squared, right? And this is equal to the KSP, that is 1.1 times 10 to the power of negative 11. So what we get over here is we get 4x cubed is equal to 1.1 times 10 to the power of negative 11. So what does x come out to? So here we get 1.40 times 10 to the power of negative 4. Okay, so that is the solubility, 1.40 times 10 to the power of negative 4 moles per decimeter cube. That's how much would dissolve to give this equilibrium constant here, right? Here we have question number 3. The energy cycle shown can be used along with suitable data to calculate the enthalpy change of hydration of calcium 2 plus. Okay, so the enthalpy change of hydration is when we go from the gaseous ions to the aqueous ions, right? Each arrow indicates a transformation W, X, Y, and Z. Each transformation consists of one or more steps. The following data and data from the data booklet should be used. Calculate the value of the enthalpy change corresponding to transformation W. Show your working. So what is transformation W here? Okay, for W you're going to look at two things. You have calcium and you have chlorine. And when you look at calcium, you're going from solid calcium to calcium 2 plus gaseous ions. Okay, so first if you're going from solid calcium to gaseous atoms, right, that's the atomization of calcium, and you have 1 mole of calcium over here, so that's just 1. So you just have 1 times the enthalpy of atomization. But you're making calcium 2 plus gaseous ions here. So you have the first ionization energy. Okay, you have the first ionization energy. And you have the second ionization energy. Okay, and you have the second ionization energy. Now, if you look at chlorine, what do you have for chlorine? Now, for chlorine, what you have here is this. Again, you have chlorine, you have gaseous molecules of chlorine, okay, that are being converted into the gaseous ions. Okay, again, you have 2 moles of gaseous ions here. Now, that's first you're going to convert them to atoms, and then you're going to form the anions. Now, for the conversion of atoms, we have 2 times the atomization of chlorine, but we don't have 2 times the atomization of chlorine. But since you have gaseous chlorine molecules, right? Since you have gaseous chlorine molecules, 2 times the atomization of chlorine is just the bond energy of ClCl. Okay, so what you have is you have the ClCl bond energy. Okay, that will make the gaseous atoms. You make 2 moles of the gaseous atoms, right? 1 mole of covalent bonds broken will give you 2 moles of gaseous atoms. Plus, you have the electron affinity of chlorine, right? But here you're forming 2 moles of 1 minus ions, so it will be 2 times the first electron affinity of chlorine. It will be 2 times the first electron affinity of chlorine. Okay, so what we have over here is, we look at transformation W. Look at transformation W here. This is what you have. Okay, this is what you have for transformation W. Okay, W is when you add up all of these together. So we can say over here, right, that W is equal to, we have atomization of chlorine. Okay, we have atomization of chlorine, or atomization of calcium, sorry, which is given to us. That is 193. Okay, we have the first ionization of calcium, the first ionization energy from the data booklet. Obviously, the data will be given to you in this exam, right? Because you won't have a data booklet. But the first ionization energy is 590 kilojoules per mole. The second ionization energy is 1150. Okay, the bond energy of chlorine is 242. Okay, and the first electron affinity is negative 349. We have 2 times that, so we have 2 times negative 349. So what is W equal to? So W comes out to positive 1477 kilojoules per mole. Okay, we have positive 1477 kilojoules per mole. Use your answer to A part 1 and other data to calculate the value of the enthalpy change corresponding to transformation Z. Okay, so Z over here, okay, we can say over here that W plus Z, right? If you start here, if you go W and then you go Z, that is the same as saying X plus Y. That is the same as saying X plus Y. So if you were starting with the elements, you can either first convert them to gaseous ions and then form the aqueous solution, or you can start with the elements, make the solid, and then make the aqueous solution. Now, what is enthalpy change X when you go from elements to solid over here? What is the enthalpy change X over here? X is the enthalpy change of formation of calcium chloride, right? We're forming calcium chloride from its constituent element. So X is minus 795. Okay, X is minus 795. That's the enthalpy change of formation of calcium chloride. And if you're dissolving the solid to form an aqueous solution, what enthalpy change is that? 1 mole of a solid dissolving to form an aqueous solution. That is the enthalpy change of solution. That is negative 83. right? That is negative 83 over here. So here we can say, again, in this case over here, we can say that x plus y is equal to w plus z. Now w was 1477, z is what we have to find, okay? Z is what we have to find, and x was the enthalpy change of formation, which is negative 795, and y was the enthalpy change of solution, that's negative 83. So here we have minus 795 minus 83. So what does z come out to? Z comes out to negative 2355 kilojoules per mole. Okay, that is negative 2355 kilojoules per mole. Use your answer to A part 2 to calculate the enthalpy change of hydration of calcium 2 plus. Now Z over here is the enthalpy change of hydration of calcium 2 plus 2 times the hydration of Cl minus. Since we're dissolving 1 mole of gaseous calcium ions to form aqueous ions, and we're dissolving 2 moles of chloride ions, gaseous ions, to form aqueous ions. So what we have is delta H hydration. Okay, what we have is this over here. Okay, this is transformation Z over here, right? This is Z, and Z is negative 2355. The hydration of calcium is what we have to find. Let's call that X, plus 2 times the hydration of chloride, which is equal to 2 times the hydration of chloride over here is negative 364. So we have over here plus 2 times negative 364. So what does X come out to? X comes out to negative 1627 kilojoules per mole. Okay, so that is the answer here. Write an expression in terms of W, X, Y, and or Z to show how the enthalpy changes of two of the transformations can be used to calculate the lattice energy. Now, by definition, for the lattice energy, we're going from gaseous ions to solid lattice. We're going from gaseous ions to solid lattice. That is the lattice enthalpy, right? Now, for two of the transformations, we have to use two of the transformations here. So, if you're starting with gaseous ions, what's one thing you can do here, right? You can go minus W, you can go minus W plus X, right? That's one possibility. Minus W plus X, that's X minus W, right? Gaseous ions form the elements and then go to the elements, and then from elements to solid, right? So that's X minus W. Or we can go Z, over here, right? And then we can go minus Y, right? So we can either have X minus W or we can have Z minus Y. Both of them will get us to, right? Starting here again, we can either go minus W and then X, or we can go Z and then minus Y, right? So our two possibilities over here are, we can either say X minus W, okay, or we can say Z minus Y, okay? Both of them are acceptable. State whether the lattice energy of calcium chloride is more or less exothermic than the lattice energy of magnesium fluoride. Explain your answer. Here the charges are the same, but magnesium and fluoride are both smaller ions. Okay, so for calcium chloride, will it be less exothermic or more exothermic? We have larger ions here. It will be less exothermic. Less exothermic because Ca2 plus and Cl minus are larger ions, okay, or have a greater ionic radius than Mg2 plus and F minus respectively. Okay, the charges are obviously the same. Over here, guys, again, because these ions are larger, they have a smaller charge density because the charges are the same. Okay, lattice energy, the more exothermic it is, the stronger the ionic bonds. Okay, the less exothermic means they have weaker ionic bonds, relatively speaking. So the ionic bonds in calcium chloride aren't as strong as the ionic bonds in magnesium fluoride. Okay, The sulfates of the group 2 elements vary in solubility down group 2. Give the names of two solutions that can be mixed to form barium sulfate. So here we have to mix two soluble salts, okay, together, or two solutions together to form barium sulfate. So a soluble solution for barium will always be barium nitrate, okay, because all nitrates are soluble. So you can use barium nitrate, okay, but you have to give the names here. So we will say barium nitrate, okay, barium nitrate, and if you have to use a soluble sulfate, okay, you can say potassium sulfate, because again all potassium salts are soluble, okay. So if you're not sure about what salts to use, remember that all nitrates are soluble. So if you need the barium cation, just use barium nitrate. And if you're not sure about which sulfate is soluble, always remember that potassium salts are always soluble. So you can just say potassium sulfate here. State and explain how the solubilities of the sulfates of the group 2 elements vary down the group. Now the solubility of the sulfates, okay, down the group decreases, okay. It's the opposite of hydroxide. So solubility of the sulfates of group 2 sulfates, okay, decreases down the group, okay. And the reason why is because the delta H solution, okay, the delta H solution becomes more endothermic, okay, more endothermic. And the reason why is because when you go down the group, okay, what happens is that delta H lattice, okay, the lattice enthalpy and the hydration enthalpies of the ions, okay, both become less exothermic, okay. But in this case, because solubility is not being favored, the hydration enthalpy changes by a greater amount, okay. Okay. However, we can say here that, however, okay, the delta H hydration changes by a greater amount, okay, or it decreases by a greater amount in magnitude. Okay, so the change in delta H hydration is greater. Okay. If you want to see this visually, what do we have here? Okay, what we have is this. We have, let's say, solid, okay, we have the solid, we have gas, and we have aqueous, okay, we have aqueous. Solid to aqueous is solution, okay, solid to aqueous is solution, and gas to solid is lattice. So we have that delta H lattice, okay, gas to aqueous is hydration, and solid to aqueous is solution. So what's happening is that both of these arrows, lattice and hydration, both of these arrows are getting smaller down the group. They're both getting smaller down the group. They're both getting less exothermic because you have larger ions. However, the change for hydration is greater. So this arrow decreases by a greater amount, so the delta H solution becomes more endothermic. So here, for example, if the change here is greater, the net effect that you have is you have a more endothermic delta H solution, okay, because the change for hydration is greater. All right. So here we have question number 4. It says identify the substances liberated at the anode and at the cathode during the electrolysis of saturated KCl aqueous. Now, if you have saturated potassium chloride, you guys remember for the liberation of oxygen at the anode, right? The potential that we have is negative 1.23. Whereas for chlorine gas, we have negative 1.36 volts. But this is obviously if you have a 1 mole per dm cube solution of chloride. Now, since the difference between this is very small, since the formation of chlorine is just, the difference between these is just 0.13. Oxygen is favored in a dilute solution, okay, or a 1 mole per dm cube solution. But if you have a concentrated chlorine solution, then or concentrated solution of chloride, then instead of oxygen being liberated, chlorine gas is liberated. Okay, so at the anode we have chlorine, okay, gas, and at the cathode, right, you have a choice between the formation of hydrogen gas and potassium, right? Since you have either H plus ions undergoing reduction or K plus undergoing reduction, and we know that potassium pretty much never undergoes reduction. Okay, it can never compete with H plus because it's a highly reactive metal, so it wants to remain in the oxidized form. K plus doesn't really go back to potassium. So here, okay, hydrogen gas will be liberated since hydrogen gas is not nearly as reactive as potassium metal. When dilute sulfuric acid is electrolyzed, oxygen is liberated at the anode. Dilute sulfuric acid is electrolyzed for 15 minutes using a current of 0.750 amperes. Calculate the volume of oxygen that is liberated under room conditions. Now here, for the liberation of oxygen gas, we have the following half equation. Right? We have 2H2O. We have 2H2O making oxygen gas plus 4H plus 4 electrons. And we want to know the volume of oxygen gas produced, right? Now, under room conditions. Now, given that we have the charge over here, we can figure out the number of moles of electrons. And from that, we can figure out the number of moles of oxygen gas and therefore the volume. Now, in order to figure out the number of moles of electrons, we first need to figure out the charge, right? Now we know that the charge is equal to the product of current and time, right? We have Q is equal to IT. And what we have over here is the current is 0.75 amperes, okay? And the time that we have is 15 minutes. So in seconds, that's 15 times 60. So that gives us a charge of 675 coulombs. Now we know that 1 mole of electrons, has a charge of 96,500 coulombs, right? That's Faraday's constant. So how many moles of electrons will have a charge of 675 coulombs? Here we know that charge obviously depends on the number of moles of electrons or the number of electrons that are exchanged in this process. So here we have the formula Q is equal to NF. You can use that formula where Q is the charge, N is the number of moles of electrons, and F is Faraday's constant. Or you can use this unitary method here. And here if we calculate N comes out to 6.99 times 10 to the power of negative 3 moles of electrons. So that's how many moles of electrons we have. So now that we have the number of moles of electrons, right, we have the number of moles of electrons over here as 6.99 times 10 to the power of negative 3 moles. So we can say that the number of moles of oxygen, we can say over here that the number of moles of oxygen is equal to the number of moles of electrons divided by 4. Because for every 1 mole of oxygen gas, 4 moles of electrons are released in this half equation. So therefore, the number of moles of oxygen is 1.75 times 10 to the power of 3 moles. And for the volume of oxygen in centimeter cube, that's just the number of moles times 24,000 centimeter cube, since 1 mole of oxygen gas occupies 24,000 centimeter cube under room conditions. So that gives us the volume of oxygen as 42.0 centimeter cube. The next part of the question says, the halogens, chlorine, bromine, and iodine differ in their strengths as oxidizing agents. These strengths are indicated by the E0 values for these halogens. Give the E0 values for chlorine, bromine, and iodine acting as oxidizing agents. So here, from the data booklet, we have these 3 half equations. We have these 3 half equations for the halogens acting as oxidizing agents. In other words, over here, they're gaining electrons, right, undergoing reduction, acting as oxidizing agents. And the E0 values that we have is for chlorine as an oxidizing agent is plus 1.36 volts, right? So for chlorine, what we have is, we have plus 1.36. For bromine, it's plus 1.07. And for iodine is plus 0.54 volts, okay? The next part of the question says, deduce which of chlorine, bromine, and iodine will react with a solution of SN2 plus under standard conditions. Explain your answer. Include a relevant equation in your explanation. Now we have chlorine, bromine, and iodine. They're oxidizing agents, so they will undergo reduction. So the half equations as they're shown will be the half equations for the halogens. If they're reacting with tin2, since they're oxidizing agent, tin2 will be oxidized. In other words, tin2 will lose electrons. So if we're starting with SN2 plus, right, the oxidized form of tin in this case, if you look at the half equation from the data booklet, what we have is, here we have the half equation that contains SN2 plus and an oxidized form of tin, right? We have SN2 plus and the oxidized form of this would be SN4 plus. Again, we know over here, we're not going to use the tin metal half equation because we know for a fact that since we have halogens and they're oxidizing agents, the halogens are oxidizing agents, they're going to undergo reduction. And since they're oxidizing agents, they're going to oxidize tin to Sn2 plus to Sn4 plus. So the equation that we have over here for the oxidation, or the half equation that we have for the oxidation of Sn2 plus, is this equation here. Sn2 plus will oxidize to form Sn4 plus 2 electrons. And the electrode potential for this is negative 0.15 volts, since we're taking the reverse reaction here. Now, we want to know which of these will react with Sn2 plus. In other words, we want to know which of these halogens will be able to oxidize Sn2 plus. Now, if you notice, the oxidation of Sn2 plus to Sn4 plus has an EMF, okay, or an electrode potential of negative 0.15 volts. Whereas if you take any of the halogens here, let's use X to represent the halogen. If you take any of the halogens, when we talk about their reduction, right? When we talk about the reduction here, right? So they'll undergo reduction to form the halides, right? No matter which halogen we use, right? This positive value here in magnitude is greater than 0.15, whether you take 0.54, whether you choose iodine, whether you choose bromine, or whether you choose chlorine, right? This magnitude is going to be greater than negative 0.15. So over here, what we know is that for the overall equation, what we're going to have is, we're going to have Sn2 plus reacting with the halogen to form Sn4 plus and the halide ions. And no matter which halogen we choose, right, the EMF of the cell over here will always be greater than 0. Okay, the EMF of the cell will always be greater than 0, since this positive value in magnitude will always be greater than this negative value. This positive value in magnitude is always greater than this negative value. So what we can say over here is that no matter which halogen we use, they'll all be able to react with Sn2 plus. So the answer over here is that all of them will react with Sn2 plus, because for all of them, okay, because the E naught of the cell is greater than 0 for all of them. Okay. An excess of chlorine is added to a solution of acidified manganate ions under standard conditions. Give the formula of the product of this reaction that contains manganese. Now in this particular reaction, we're using chlorine as an oxidizing agent, right? And that the EMF, or the standard electrode potential for that is, the E naught for that is plus 1.36 volts. Now when we talk about Mn2 plus in acidic conditions, right, what we see over here is we see the following half equations. Again, for chlorine, what we have is we have a plus 1.36, and since chlorine is the oxidizing agent, we know that the Mn2 plus over here will undergo reduction. So we're looking at the backward reactions for these half equations, since Mn manganese will be losing electrons. Now, what we see over here is this is plus 1.36. Okay. On the other hand, for manganese, what we see over here is this. If you're starting with Mn2 plus, as your starting reactant, right? For the oxidation of Mn2 plus, again, chlorine is the oxidizing agent, so Mn2 plus will undergo oxidation, since chlorine will undergo reduction here. Right? For the oxidation of Mn2 plus, if you look at the backward reaction, right, you have a potential of negative 1.23 volts. So the overall reaction will be plus 1.36 minus 1.23. So the overall EMF will be positive. So this will be a spontaneous reaction, giving us the product MnO2. Now, MnO2 over here cannot be further oxidized by chlorine, because for the oxidation of MnO2, again, we're looking at the backward reaction, right? The electrode potential is negative 1.67 volts. Now, reduction of chlorine is plus 1.36 and oxidation of MnO2 is negative 1.67. So plus 1.36 minus 1.67 will give us a negative EMF for the cell. So chlorine will oxidize Mn2 plus to MnO2, but it won't be able to oxidize MnO2 to MnO4 minus. nor can chlorine oxidize Mn2 plus directly to MnO4 minus, because for the oxidation of Mn2 plus to MnO4 minus, we'll have a standard electrode potential of negative 1.52 volts. So again, Mn2 plus will not be oxidized to MnO4 minus, since the reduction of chlorine here will be plus 1.36 volts, whereas the oxidation of Mn2 plus directly to MnO4 minus is negative 1.52, plus 1.36 minus 1.52 will again give us a negative EMF for the cell. So here chlorine can oxidize manganese. It can oxidize manganese to MnO2, but it won't be able to oxidize MnO2 further to MnO4 minus, nor will it be able to oxidize Mn2 plus directly to MnO4 minus. So the final product over here will be manganese 4 oxide. All right. Next part of the question says an electrochemical cell can be made by connecting an Fe3 plus Fe2 plus half cell to an S2O8 minus SO4 minus half cell under standard conditions. Calculate the standard cell potential of this electrochemical cell. So here we have the two half equations for the two half cells. And what we have is obviously the half equation in the data booklet are for the reduction, okay, of these guys over here. We have S2O8 minus being reduced to sulfate, and we have Fe3 plus being reduced to Fe2 plus. Now if you look at the electrode potentials for these half cells, we see over here that the reduction of S2O8 is way more favored than the reduction of Fe3 plus. So if we connect these two half cells together, we know for a fact that S2O8 will undergo reduction, since the electrode potential for this is positive 2.01, whereas iron 3 won't undergo reduction. Instead, iron 2 will be oxidized. Iron 2 will be oxidized. So here the reverse reaction will take place that will have a potential of negative 0.77 volts. So here the forward reaction will take place, and this reaction shown here, S2O8 minus will undergo reduction, whereas iron 2 will undergo oxidation. And the overall EMF for this cell will be plus 2.01 minus 0.77, so that will be 1.24 volts. State the material that should be used as the electrode in each half cell. Now for each of these half cells, we have two aqueous species. So the electrode material that we're going to use will be platinum. We always use platinum electrodes. Unless there is a metal involved in the equilibrium. Here we have two aqueous ions, here we also have two aqueous ions. Whenever there's only aqueous species, or we have gaseous species, or we have liquids, okay? In all of those cases, we're going to use a platinum electrode. The only time we're going to use a metal electrode other than platinum is if there's a metal in one of the equilibria or in one of the half cells, then we're going to use that metal as the electrode. Otherwise, it'll always be the inert platinum electrode. Describe one change to each half cell that would increase the value of the cell potential. The temperature should remain at 298 Kelvin. So here, the question is asking if we had each half cell, we want to increase the value of the cell potential. In other words, we want to increase the EMF of the cell. We want to make it more positive than 1.24. Now there's two ways of doing this. We can either make this half equation more positive. To make this half equation more positive, we have to shift this equilibrium to the right. Now this equilibrium can shift to the right if I increase the S2O8 minus concentration, or if I decrease the concentration of the product here, which is the sulfate ion. So I can either decrease the concentration of SO4 minus, or I can increase the concentration of S2O8 minus. Those are the potential changes I could make to this half cell to make this electrode potential more positive, shift the equilibrium to the right, and therefore make the EMF of the cell more positive. What about the other electrode? Now for the other electrode, right, on the other electrode, the reaction that's taking place is the oxidation of Fe2 plus to Fe3 plus. And here our potential was negative 0.77 volts for that half cell. right? Now over here, if I want a more positive cell potential, or I want to increase the cell potential, so I want a more positive EMF, I have to make this less negative. Since we're subtracting this from this, I want to make this less negative. In order to make this less negative, right, I want to shift this reaction to the right. Now I can do that by either increasing the concentration of Fe2 plus or decreasing the concentration of Fe3 plus. So I can either increase the concentration of Fe2 plus, or you can decrease the concentration of Fe3 plus. Here we have question number 5. Define the term transition element. Now, a transition element can be defined as an element that forms at least one stable ion that has a partially filled d subshell. Or you can say it has partially filled d orbitals. Now, note that this definition is just the Cambridge definition. Okay, the actual definition by chemists has been revised. So if you do look it up, you'll see a different definition, but this is the definition that they want for your CAIE exams. Complete the electronic configuration of an isolated gaseous Fe3 plus ion. Now over here, iron has the atomic number 26. So iron has 26 protons, an atom of iron has 26 protons. So therefore, if you look at an iron atom, it has 26 electrons. So if you look at the periodic table, right, the electronic configuration over here is argon, right, and then we have 3d6 4s2. Right, this is the shorthand or the short form of the configuration. For the Fe3 plus ion, the outer 3 electrons are lost. So if you remember, first the 4s2 electrons are lost, and then one electron from the 3d is lost, leaving us with argon 3d5. So what we have over here is, for the configuration, we have 1s2, 2s2, 2p6, 3s2, 3p6, that's argon, and then we have 3d5. Name two transition elements whose isolated gaseous atoms have the same number of electrons in the 3d subshell as an isolated gaseous Fe3 plus ion. So we need to figure out two atoms, two transition element atoms that have 5 electrons in the d subshell, so that have 3d5 in their configuration. Since we want to know two atoms that have the same number of electrons in the 3d subshell. Now, if you remember, one of the exceptions that we learned about was chromium, that instead of 3d4 4s2, chromium was 3d5 4s1. The reason why was because instead of 3d4 4s2, 3d5 4s1 was preferred, because the half-filled configuration was more stable because all the electrons were unpaired. So chromium, and then the other one that we have is manganese, which ends with 3d5 4s2. Cobalt-2 sulfate is added to water to form a pink solution containing complex ion P. So in water, cobalt-2 exists as cobalt hexa-aqua, right? And we have this 2 plus complex ion. This is a pink solution. Okay, this is P. Okay, this is P, and this is a pink solution. An excess of concentrated hydrochloric acid is added to the solution to form a blue solution containing complex ion Q. Now when we add hydrochloric acid, what we have is we have chloride ions over here. So we have a ligand exchange reaction take place, and we know that we make cobalt chloride. And cobalt chloride, we have cobalt-2 chloride, and since chloride is 1 minus, right, we have 4 chlorides, and since cobalt is 2 plus, the overall is 2 minus 4, so the overall charge is 2 minus, and we have 6H2O. So we have a ligand exchange reaction take place. If you guys remember, cobalt-2 chloride is a tetrahedral, or has a tetrahedral shape. So the shape over here looks like this, and the charge on this complex ion is 2 minus. The type of reaction taking place over here is ligand exchange. Explain why solutions that contain transition element ions are often colored. Now over here, if we remember, what happens is that in transition elements, when you have d orbitals in complex ion, the d orbitals are split into two different energy levels, into two different sets with different energies, right? And we have the difference in energy between the two sets of d orbitals corresponds to a certain frequency of visible light, okay, that is absorbed. So electrons are promoted from this lower energy d orbital to the higher energy d orbital. Since the d orbitals are partially filled here, right, electrons can be promoted from lower to higher energy, and the frequency of light absorbed is in the visible region. So for example, if you throw white light, right, that has all the different colors, all the different frequencies of visible light, some of the frequencies will be absorbed, leave to promote that electron from lower to higher energy, leaving us with the remaining frequencies or the remaining color to be observed. That is known as the complementary color. So here what we can say is that the d orbitals are split, okay, into two different sets with different energies with different energies. The difference in energy, we call that delta E. The difference in energy corresponds to a certain frequency of visible light, a certain frequency of visible light, certain frequency of visible light that is absorbed, okay, resulting in, okay, that is absorbed, resulting in an electron being promoted, okay, resulting in the promotion of an electron, or we can say excitation of an electron, from lower energy to higher energy d orbital, from a lower energy to a higher energy d orbital. And since a certain frequency of visible light is absorbed, right, the complementary color is observed. Certain colors are absorbed, so certain colors are therefore observed. So the remaining colors are observed. So the complementary color is observed. Explain why the colors of P and Q are different. In different complexes, the delta E can be different. The difference in energy between the two sets of d orbitals can be different. So the delta E is different. Okay. And if the delta E is different, it means that we can say therefore different frequencies of visible light are absorbed. Different frequencies of visible light are absorbed. And if different frequencies are absorbed, obviously different frequencies or different colors will be observed. A solution of the bidentate ligand 1,2-diaminoethane is added to an aqueous solution of cobalt 2 sulfate. Oxygen is then bubbled into the mixture, forming a complex ion with the formula given over here. Here in this, we have three bidentate ligands bonded to the cobalt over here. And we form a 3+ ion. This complex exists as a mixture of two isomers. The geometry of both of these isomeric complexes is octahedral. Since we have three bidentate ligands, right, there's 6 dative bonds. Each bidentate ligand is making 2 dative bonds to the central cobalt ion here. In this reaction, cobalt undergoes two types of reactions. One type is the same as described in C part 2. Name the other type of reaction. Now in C part 2, we had a ligand exchange. And here, obviously, if we have an aqueous solution of cobalt 2 sulfate, we have cobalt hexaaqua, right? So we have cobalt with 6 water molecules around it in the aqueous solution. That's the pink solution. And those water molecules are replaced by 1,2-diaminoethane. So that's a ligand exchange reaction. But what we also see here is that here we had a solution of cobalt 2 sulfate. When oxygen was bubbled through the mixture, cobalt 2 was converted into cobalt 3. This complex ion has a charge of 3+. The bidentate ligand is neutral. That means that the cobalt has an oxidation number of +3 here. So cobalt was oxidized from +2 to +3. So there was a redox reaction taking place. Cobalt was oxidized, and oxygen is obviously the oxidizing agent here, and that was reduced. So in this reaction, The type of reaction that cobalt undergoes is oxidation because cobalt is being oxidized here. Draw the three-dimensional structure of the two isomeric complexes in the boxes. You may use this to represent a molecule of 1,2-diaminoethane, or we say ethane 1,2-diamine. Now over here, if we have three bidentate ligands, in an octahedral complex, okay, it shows optical isomerism. The complex shows optical isomerism. So what we have over here is this. We have this octahedral shape here, and we have this octahedral shape over here. And if we draw the, let's draw the first optical isomer on the left. So here we have three bidentate ligands like this. And then on the right, we have the mirror image of this guy over here. So on the right hand side, what we're going to have is this. We're going to have this, then we have this bidentate ligand here, and then we have this bidentate ligand here. So these two are mirror images of each other. They're non-identical mirror images of each other. So this type of stereoisomerism shown by these two isomeric complexes is optical isomerism. The coordination number of cobalt in these two isomeric complexes is 6. The coordination number is simply the number of dative bonds made to the central metal ion over here. It's obviously good to write down the charge of the complex ion here as well. So we have these two 3+ complex ions. The stability constants of 3 complexes of mercury 2 are given in the table. Write an expression for the stability constant of AgCN4 2-. Now for the stability constant, right, by definition the stability constant is the equilibrium constant that shows the formation of the complex ion from its constituent ions. So over here we have the central metal ion and we have the cyanide ion, that's our ligand, okay, and we have 4 of those to form over here AgCN4 2-. And the stability constant over here obviously will just be the products divided by the reactants. So what we have over here is we have the concentration of AgCN4 2-, right, divided by the concentration of Ag2+ times the concentration of cyanide to the power of 4. An aqueous solution containing Ag2+ is added to a solution containing equal concentrations of cyanide ions, chloride ions, and iodide ions. The mixture is left to reach equilibrium. Predict which of the complexes is present in the resulting mixture in the highest concentration and which is present in the lowest concentration. Explain your answer. Now they've given us the stability constants for each of these complexes. Right? We have equal concentrations of cyanide, chloride, and iodide, and all of them will form a complex with Ag2+. Now, by definition, the stability constant is a ratio of the complex to its constituent ions. So in this particular case, what we have is the larger the stability constant, the more likely that complex is to form. You're starting with the same concentration of each of these ligands. And we know that since the cyanide complex has the largest stability constant, it means that this complex is the most stable or is the most likely to form in the mixture. So therefore, we're going to have the highest concentration for the cyanide complex over here since it has the largest stability constant. We're going to have the lowest concentration for the chloride complex over here because that has the lowest stability constant. So we can say over here that the highest concentration will be for this complex, right? We have the HgCN4 2- complex, and the reason why is because it has the largest stability constant, and the lowest concentration will be for the chloride complex, that is AgCl4 2-. And the reason why is because this has the smallest stability constant. So here we have question number 6. Ethanoic acid and trichloroethanoic acid are both carboxylic acids. Ethanoic acids can be used to make ethanamide. Place these three compounds in order of acidity, starting with the least acidic. So which over here is the most acidic? Trichloroethanoic acid is the most acidic. Generally speaking, guys, whenever you have more electron withdrawing groups, okay, what it does is the withdrawal of electrons, okay, it weakens the OH bond. Or you can say that if you have the conjugate base over here, right, the conjugate base is more stable, so the acid is more likely to remain dissociated. Okay, so what we have over here is that the most acidic is trichloroethanoic acid, okay, because it has 3 electron withdrawing chlorine atoms, followed by ethanoic acid, okay, because that's still an acid, whereas ethanamide is actually not acidic or basic, right? Amides are neutral. So ethanamide is the least acidic over here. Okay, and you would, if you had to explain this again, you would say that okay, if you look at trichloroethanoic acid, you have CCl3 CO2H. Okay, it has 3 electron withdrawing chlorine atoms. Okay, therefore we can say that the conjugate base is more stable. So the CCl3 CO2 minus ion is more stable. Okay, that's the conjugate base. So that means that it's the most acidic. Okay, and we know that ethanamide, okay, is not acidic. It is a proton donor. It is not a proton donor, sorry. Okay, it is not a proton donor. Here again, ethanamide is actually neutral. Okay, it's not acidic or basic. Amides, amines are basic. Amines are basic because the nitrogen wants to accept a proton. They're not acidic. On the other hand, if you have an amide, okay, the oxygen atom withdraws electron density, making amides non-basic and obviously not acidic either. Okay, so it's neither in this case. Whereas ethanoic acid is still an acid, but it's a weaker acid than trichloroethanoic acid. Okay, all right. Methanoic acid and ethane dioic acid are two other carboxylic acids. State which, if any, of ethanoic acid, methanoic acid, and ethane dioic acid will react with Felling's reagent. Which of these will react with Felling's reagent? Felling's reagent is for the CHO group. Methanoic acid here, okay, methanoic acid has the CHO group. Okay, methanoic acid has the CHO group. Okay, Felling's is not just for aldehyde, it is for the CHO group here. Okay, so because methanoic acid has a CHO group, okay, that will react with Felling's reagent. So it's only methanoic acid here. Okay, the others don't have a CHO group. State which, if any, of ethanoic acid, methanoic acid, and ethane dioic acid will react with warm acidified manganate ions. Which of these three undergo oxidation with acidified manganate? You guys may have learned that both ethane dioic acid and methanoic acid are oxidized to carbon dioxide and water. Okay, so what you have here is we have methanoic acid, okay, and ethane dioic acid will both be oxidized. Ethanoic acid won't. Okay, ethanamide can be made from ethanoic acid in a two-step synthesis. Compound A contains chlorine. Give the structural formula and name of A. So, what are we converting the acid into? What type of a compound would this be? We have CH3, C double bond O, OH. We are converting this into some chlorine compound. We're converting it into an acyl chloride. We're converting this into an acyl chloride. Okay, so the structural formula for this would be CH3COCl, and the name for this compound is ethanol chloride. All right, moving on. Suggest suitable reagents for step 1 and 2. For step 1, if you want to convert ethanoic acid to an acyl chloride, we can just use PCl5, or you can use SOCl2. Okay, and if you want to convert this into an amide, if you want to convert the acyl chloride into ethanamide, right, you're forming C double bond O NH2. So what's happening here is you're reacting this with ammonia, right? You have a condensation reaction take place where HCl is removed, right, and you form an amide linkage between this carbon and this nitrogen. Okay, so you're going to need ammonia for the second reaction. Okay. Compound A can be used to make the amide CH3CONH C2H5. The proton NMR spectrum for this amide in the solvent CDCl3 is shown. Explain why CDCl3 is used as a solvent instead of CHCl3. CDCl3 over here is hydrogen 2, whereas this H over here represents hydrogen 1. Now, if you guys remember, if there's an even number of nucleons, it doesn't show up in the NMR spectrum. Odd number of nucleons, right? Here we have an odd number or an odd nucleon number, right? Or odd mass number, it will show up in the NMR spectrum. You don't want the solvent to show up. You only want the main thing to show up. You don't want the solvent to show up. So therefore we use CDCl3 because it has an even mass number. The solvent itself won't show up in the NMR spectrum. Okay, so it won't give a signal. Okay, does not give a signal. Okay, give a signal in the NMR spectrum. Complete the diagram with the chemical shifts of the protons labeled in this molecule. Okay, so we have this molecule of CH3CONH C2H5. Okay, and we have to give the chemical shifts over here. So here we have the table of the chemical shifts. Okay, here we have the table of the chemical shifts, and we have our molecule. Okay, and we have our molecule over here. So here I have the table again, and I'm just going to draw the molecule over here. Okay, by the spectrum, what we have is we have CH3, C double bond O, NH, and then we have a CH2, CH3. Now let's start one by one, right? If you look at the CH3 on this left hand side over here, which of these peaks would be that CH3 over here? Which of these peaks would be that CH3 over here? If you look at the table, right, you have a CH3 next to a C double bond O. Okay, that would be around 2.2 to 3. That would be around 2.2 to 3 over here. Okay. Now here we also have an amide linkage, right? There isn't really any peak shown for the amide linkage directly, but what's the only peak that we have anywhere close to this range? What's the only peak that we have anywhere close to this range? It'll be this guy over here, right? If we call this HA, right, that's this guy over here. Okay, so HA is around 2. Again, the CH3 C double bond O is not for the amide linkage. It's for like if you have like an aldehyde or a ketone, right? But with an amide, it'll be slightly lesser, right? So it's around 2, but it's very close to that. Okay, because it's directly bonded to a C double bond O, and it's a singlet. It's a singlet over here. That's the important thing to remember as well. Okay, this won't split. So you see a singlet over here because the neighboring carbon doesn't have any hydrogens. Okay, now on the other hand, if you look at this CH2 here, right, this is going to be the quartet, right? CH2 is split into a quartet. CH2 is split into a quartet by the neighboring CH3. So this is HB. And if you call this HC, the CH3 is split into a triplet by the CH2. And obviously CH3 is the alkyl group. So that's around 0.9 to 1.7. Okay. So here you have HC, right? What you have is Whenever you see a triplet quartet, it's because of the CH2, CH3. So here you see a triplet quartet, right? This quartet, CH2 quartet, is because of the neighboring three protons. Neighboring three protons mean it's split into 4, okay? And it's around 3.3, right? Which is consistent with alkyl next to an electronegative atom. And the CH3 is split into 3 by the neighboring 2 protons. That's the triplet, and that's the alkyl group in the range 0.9 to 1.7. Here it's around 1.3. Okay. And then the last proton that we have left over here is the NH proton, right? Let's call this HD, and that'll obviously be this guy over here. Okay. And you can look at that in the table, right? You can look at that in the table. If you have an NH proton, right, it is going to be, the amide is in a very broad range of 5 to 12. So that's the one we determined at the end. Okay, and this is the only proton that we have in that range, in the range 5 to 12. So this must be the amide wala proton. Okay, the nitrogen wala proton, the proton on the nitrogen. So what we have over here is, okay, if you look at the values, over here, the CH3 next to the C double bond O is around 2. Okay, it's around 2 parts per million. Okay, then the NH peak over here is, around 6.8. Okay, around 6.8 parts per million. Okay, this is estimate. They'll accept, there's a broad range that they'll accept, okay, between 6.5 and 7. Okay, the CH2 proton that we have is around 3.3. It's around 3.3. Okay, and the last one that we have is around 1.3. Okay, so these are the 4 peaks that we have. Right, that's the 1.3 over here, that's the CH3. Okay, again guys, this range of 2.2 to 3, yes, this is not between 2.2 to 3, but these ranges are approximate. You're looking for close to that range sometimes as well. Okay, they won't necessarily always fall exactly in that range. This C double bond O is not a standalone C double bond O, it's part of an amide linkage, so this nitrogen is affecting it. You don't need to know how it's affecting it, but it's going to be slightly off that 2.2 over here. In this case, it's around 2. Okay, even if you weren't sure about this, you can easily deduce the other 3. You know that if you have a triplet quartet, it will be these 2, right? This is the alkyl group clearly, and it's going to be a triplet. And this is a quartet, definitely bonded to the nitrogen, bonded to an electronegative atom. So it's around 3.2 or 3.3. We were able to deduce this, and then you have 2 singlets left, either this one or this one. Now there's 2 ways to identify which one is this guy. First of all, this one will be taller because this is 3 protons, this is 1 proton. So we easily know that this one is the CH3 here, whereas this guy is the amine. Secondly, if you look at the range of 5 to 12, that is the amide wala hydrogen, right? The hydrogen bonded to the nitrogen in the amide is in the range 5 to 12, which is only this one over here and not this one. So you can deduce that this singlet is because of this guy, and the remaining singlet that you have is because of this guy. Okay. All right. State and explain how the proton NMR spectrum differs when dissolved in D2O rather than CdCl3. Now, when you use D2O, right, D2O displaces any protons that are bonded directly to a nitrogen or an oxygen. Any NH or OH protons, the peaks will disappear. Okay, the peaks will disappear. So in this particular case, the peak at the chemical shift 6.8 parts per million would disappear. Okay, would disappear because you have the H in the NH is substituted by deuterium, Okay, for deuterium, for proton exchange, you will use D2O, not CdCl3. D2O is what replaces that proton, okay, not CdCl3. The peak at 0 over here, okay, just as a reminder, is due to TMS. Okay, that's the reference that we use. Everything is measured relative to this TMS peak. Okay. All right. The mass spectrum of this compound includes a fragment ion with mass to charge value of 58. Give the molecular formula of this fragment ion. Okay, so what will this fragment look like? Now this guy over here, okay, it has an MR of, it has an MR of 87. Okay, so with the MR over here is 87. And if we're observing a fragment of 58, something broke off to give you a fragment of 88. Okay, and that something must have had a mass of 29. So if the ethyl group breaks off, right, ethyl has a mass of 29. If the ethyl group breaks off, you're left with this fragment over here that has a mass of 58. So the ion over here will be the CH3 CONH ion. Okay, because remember the cation shows up in the mass spectrum. So this 50, again, you had a molecule with MR 87. Okay, when the 29 breaks off, you're left with a mass of 58 for a cation. So that will be the CH3CONH ion plus ion over here. The amide undergoes the following reaction to produce diethylamine. Identify reagent B. We're reducing an amide here. So the reagent that we use for reducing amides is lithium aluminum hydride. Okay, in dry ether. Okay, it has to be anhydrous lithium aluminum hydride. State the number of different absorptions in the carbon-13 NMR spectrum of diethylamine. If you look at diethylamine, right, this is what we have. How many different types of carbon atoms do we have here? These two CH2s are identical, right, because the molecule is symmetric. So these two CH2s are identical, and these two CH3s are also identical. So you only have two different types of carbon atoms, so you will see two different peaks over here. All right. So here we have question number 7. Okay, part A says, describe the structure of a benzene molecule. Your answer should include the shape of the molecule, the relative lengths of the carbon-carbon bond, the bond angles, the hybridization, and the overlap between orbitals that produces each type of bond present. Okay, so what we have is, if you look at a benzene ring, okay, look at a benzene ring, okay, what is the shape of a benzene ring? It has a planar, okay, it is a planar molecule, okay, regular hexagonal shape, right? It's a hexagon, right? All the carbon-carbon bonds, all the carbon-carbon bonds are of equal length, okay, are of equal length. So we've included the shape of the molecule and the relevant relative lengths of the CC bonds, okay. All the bond angles are 120 degrees. All the bond angles are 120 degrees, okay, where the carbon atoms are sp2 hybridized, okay, sp2 hybridized. All right, and the overlap between orbitals that produces each type of bond present, right? You have sigma bonds between, right, carbon-carbon atoms, right, due to overlap of sp2 orbitals, okay, sp2 orbitals, and you also have a delocalized, okay, you have a giant delocalized ring of pi electrons, ring of, okay, delocalized pi electron ring or delocalized pi bond, okay, due to overlap of p orbitals. Benzene can be used as a starting material to produce phenylamine by a two-step synthesis. Okay, in the first step, benzene reacts to form nitrobenzene. In the second step, nitrobenzene is reduced to form phenylamine. Complete the reaction of benzene with NO2 plus ions. Complete the mechanism and draw the intermediate of step 1. Include all relevant charges and curly arrows to show the movement of electron pairs. So first, you have the electrons moving from the ring to this guy, okay, resulting in the formation of this carbocation intermediate. Okay, you have this carbocation intermediate form. We have an H and an NO2, and the electrons from the CH bond go back into the ring, okay, to reform the ring. Nitrobenzene and H pluses released over here. Okay. State the name of this mechanism. This is electrophilic substitution. Next part says, identify the reagents needed to produce NO2 plus ions. Write an equation to explain how these reagents produce NO2 plus ions. So what you're going to need in this reaction is, you're going to need concentrated nitric acid. Okay, you're going to need concentrated nitric acid and concentrated sulfuric acid. Okay, and the equation that you have over here is, this. You have HNO3 reacts with H2SO4, okay, to form NO2 plus, that's your electrophile, okay, and you're also forming over here, okay, H3O plus and 2HSO4 minus. So you're going to need two of these over here. Give reagents and conditions for the production of phenylamine from nitrobenzene. Okay, so that's the reduction of nitrobenzene to phenylamine. Okay, and for that you're going to use tin and concentrated HCl. Okay, and you're going to heat. Phenylamine reacts with Br2 aqueous. Write an equation for this reaction. You may use structural or displayed formula. Okay, so what you have is, if you have something like phenylamine, you have C6H5NH2. Okay, and you're gonna make tribromophenylamine. If you guys remember, you have 3 bromine atoms substitute. This is similar to what happens with phenol. Okay, so you're gonna have 3 bromines react, and you're gonna form C6H2Br3NH2, okay, plus 3HBr. Okay, you have 3 bromines substituting for 3 hydrogens on the benzene ring. Here what you're doing is, phenylamine, when it reacts with aqueous bromine, it's similar to what you have with benzene. Okay, similar to what you have with benzene. So you end up making this guy. You have Br, Br, and Br. 2,4,6 tribromophenylamine. Okay, this is what you're making here. Okay, it's for phenol and phenylamine. You're going to see a white precipitate and decolorization of aqueous bromine here. Okay, the organic product over here is tribromo. Okay, 2,4,6 tribromo, 2,4,6 tribromophenylamine. Describe two observations. Two observations that you see is, you decolorization of Br2 aqueous, or you can say brown to colorless. Okay, the solution goes from brown to colorless. Okay, and the other observation is that you see a white precipitate. That white precipitate again is this guy over here, 2,4,6 tribromophenylamine. Okay, next part over here says, describe the relative basicities of ammonia, ethylamine, and phenylamine. Starting with the least basic, explain the answer in terms of their structures. Now, if you look at ammonia, right, and ethylamine, which of these is more basic? Here, ethylamine is more basic. The reason why ethylamine is more basic is because of the electron donating effect of the ethyl group, which makes this nitrogen more negative, right? It increases the electron density on the nitrogen, making it more likely to accept a proton. Now, if you compare ammonia and phenylamine, which is more basic? Ammonia versus phenylamine. Ammonia is more basic, because in phenylamine what you have is that you have these electrons in the p orbital, the lone pair electrons delocalize into the ring, making the electrons less available for donation. So in ethylamine, relative to ammonia, the electrons are more available for donation and accepting a proton. In phenylamine, due to the resonance, right, delocalization of electrons into the ring, the electrons are less available for donation. Okay, so what you have is the least basic over here is phenylamine, okay, followed by ammonia, and the most basic is ethylamine. Okay, and the reason why is because, okay, ethylamine has an electron donating ethyl group, or you can say it has an ethyl group, okay, which has a positive inductive effect, containing ethyl group, okay, which makes the lone pair, okay, okay, more available for donation, okay, available for donation. So we can say that ethylamine than an ammonia, right? So we can say for ethylamine we have, okay, it's more likely to accept protons, okay, so it's more basic. All right, on the other hand, okay, this is the lone pair on nitrogen, obviously. On the other hand, if you talk about phenylamine, in phenylamine what you have is, okay, in phenylamine, okay, the lone pair on the nitrogen atom, is delocalized into the ring, okay, making it less available for donation, okay, making it less available for donation, okay. So phenylamine is less likely to accept a proton, less available for donation, okay. So it's less likely to accept a proton, less likely to accept proton than ammonia, okay. In general, whenever, if you want to figure out what's more basic, wherever you have the electron density increasing, the compound will be more basic, because it will more likely accept a proton. Whenever you have the electron density on the nitrogen decreasing, the compound will be less basic, okay. For acids is the opposite. Electron withdrawal increases acid strength, electron donation decreases acid strength. For bases, electron donation increases base strength, whereas electron withdrawal decreases base strength. All right, last part. 1,3-diaminopropane can be used to make polyamides. Identify one compound that would react with 1,3-diamine propane to form polyamide, right? So what you would need is, you have two amine groups over here, so you would need something that has two acid groups or two acyl chloride groups, okay, that has two acid groups or it has two acyl chloride groups. So for example, a compound that can do it would be something like this, okay. A compound that can do it would be something like this, right? Draw a section of the polymer chain formed from 1,3-diaminopropane and the compound you chose. Your answer should include 4 monomer residues, right? 2 of each type of monomer. So that means 2 repeat units. Show the amide link fully displayed. Clearly identify 1 repeat unit. So what you have over here is this. You have H2N, right? And then you have 3 CH2s. And then you have an N, H2 again, right? And then the acyl chloride that I chose over here was this guy. You have CO, and then you have a Cl and the Cl. Now, if you're making a polyamide here, right, you have condensation polymerization. You're making the amide linkage between, right, the nitrogen from the amine bonds to the C double bond O from the acyl chloride, and HCl is lost since it's condensation polymerization. So this is how you're going to make the amide linkage. And you're going to have continuation on either of these ends over here as well. So what would a single repeat unit look like? A single repeat unit would look like this. You have the NH, okay, and then you have CH2 3 times, and then you have the NH, C double bond O, right? Then you have C double bond O, right? So this is a single repeat unit. Remember, the H from this end is also lost, and the Cl from this end is also lost. So this is a single repeat unit over here, and I've clearly shown the amide linkage. Now they want 4 monomer residues, 2 of each type of monomer. Here we have 1 of each type of monomer, and then if we showed another repeat unit, right, what do we have? We have an N, H, and then we have CH2 3 times, okay, and then we have over here an NH, okay, we have an NH, and then again we have a C double bond O, C double bond O, and now this is repeating itself. So here we can clearly see a single repeat unit. Here we can clearly see a single repeat unit, right? This is what's repeating itself. Okay, this guy here then again repeats itself over here. Okay, so this is a single repeat unit, and I've also shown 2 repeat units, and I've clearly identified 1 repeat unit in this structure.